planar structure of a single crystal silicon semiconductor, you see we don't have any impurities over here, so it's a pure semiconductor or an intrinsic form of semiconductor. So what happens is that when the silicon atoms they come close to each other, they form what is known as the covalent bonds, okay, to complete their stable octet structures. And in process of this formation, an atom does achieve stability, and the electrons that are bonded with the neighboring 4 silicon atoms are they're said to be occupying a certain energy band. Okay, so you see when silicon atoms they come together to form crystals, the electron occupy a particular allowed energy bands. They're only allowed to occupy. The outermost electrons or the valence electrons, they occur in valence energy bands. Okay, so when there is no thermal energy at 0 Kelvin, all the valence electrons they occupy the valence energy band, and they are not conducting. Okay, because they are not excited, they cannot break free from the bonds. Even if you apply a small electric field, these electrons which are shared in covalent bonds, they stick to they stick in the valence energy bands. Okay, they not jump to the conduction band unless certain thermal energy is provided, so that for example electron from here breaks from the covalent bond and becomes a free electron, and then this electron is free to move around the array of or the lattice of silicon crystal, and this electron is then generated in the conduction band because it has energy, and it can contribute to the conduction of current. Okay, so but again, as we have said before, that if the electron breaks free from the covalent bond given a thermal excitation energy, the overall crystal is still neutral. Okay, there is no net charge, because depending on the number of covalent bonds that are being broken as temperature is increasing, the number of positive states that are being created where there is electron deficiency, now you have so many number of electrons. Okay, so the net there is no net charge. There is no net charge. The crystal is still is pure and it's still neutral. Okay, unless you are going to dope the crystal with some impurity and then you're going to introduce more concentration of free charge particles, and there is no net charge. Okay, so any such electron may gain enough thermal energy to break the covalent bond and move away from its original position, as schematically shown in figure 1.3 over here. So this is the breaking of covalent bond for temperatures above 0 Kelvin, when an electron jumps to the conduction band and a positively charged empty state is left behind. Okay, so in order to break the covalent bond, the valence electron must gain a minimum energy, and this energy is noted by Eg. It is called the band gap. Okay, this gap exists between, let's say, Ev, which is the valence band, where the electrons they occupy, call this the maximum energy state, where they are bonded to each other to form the complete octet structure, and then there is a conduction band, Ec. Okay, and within this, and the difference between these two is the band gap. Okay, a typical semiconductor like silicon may have a band gap of, let's say, 1 electron volts, and if we are talking of a pure silicon like this, pure silicon, single crystal silicon semiconductor material, then this band gap is all what is required for the electron to jump or let's say an electron can be generated from, let's say, can be broken from the covalent bond to, and can break free from the covalent bond and get itself to a higher state of conduction band. Okay, but it cannot stay within this band. This is forbidden band. Okay, it cannot conduct in a forbidden band. It has to get some thermal energy. It has to break free from the covalent bond, get to the conduction band, and then it is free in the crystal to conduct electric current. Okay, so the electrons that gain this minimum energy, now they exist in the conduction band and are said to be free electrons. Now these free electrons in the conduction band can move throughout the crystal, and the net flow of electrons in the conduction band generates the current. Okay, so one thing you notice over here, another thing is that it's not only the electrons they're always positive empty spaces, okay, positively charged, or call it deficient empty states, which are electron deficient, okay, from which the electron has break free. So besides the overall crystal being neutral, it's not only the electrons that are contributing to the conduction in a semiconductor material. It's also the positively charged particles, which we are going to call as holes. Okay, hole means the deficiency, and the definition is due to the electron that was bonded over here. Okay, and this is free electron. This is a free charge carrier now in the crystal, and the number of holes and the number of free charge carriers in an intrinsic or a pure semiconductor is equal. Okay, it has to be, right, so that the overall crystal is neutral, stays neutral. So you see an energy band diagram is shown in figure 1.4a over here in this figure, and you have valence band where the electrons, this is the maximum energy that the electrons can have in the valence bands, and then unless they are provided enough energy, they are thermally excited, so they jump to the conduction band where they start conducting, leaving empty valence states, positive states, holes behind. They cannot conduct, and they cannot stay over here. This is the forbidden band. Unless they get enough thermal energy to break free from the covalent bonds, they get themselves free in the conduction band and start conducting. Okay, so the energy EV is the maximum energy of the valence energy band, and EC is the minimum energy of the conduction band. So over here you see this EV is the valence band energy, EC is the conduction band energy, and the difference is the forbidden gap. Okay, now this forbidden gap is in a typical insulator, it can be more than, for example, 3 electron volts, typical 3 to 6 electron volts, which means that for an insulator you don't have much thermal energy at room temperatures, ordinary temperatures, to provide free charge carriers. I mean, the electrons are bonded in a compound and they cannot break free even with the application of small electric field or temperature. So they cannot break free from the bonds and they cannot contribute in the conduction. However, in a semiconductor, this forbidden gap is small as compared to insulator. It could be in semiconductor, the band gap energy is in the order of 1 electron volt, and it can easily conduct given the thermal energy is there for excitation. For metals, for conductors which have a very large number of free electrons, there's no such problems, and that's why they are called conductors, and they conduct at ordinary temperatures. Okay, so in contrast, materials that contain very large number of free electrons at room temperature are conductors. So material having large band gaps in 3 to 6 electron volts are insulators, and because at room temperature essentially no free electrons exist in the conduction band. So you can explain these things, the differences between insulator, conductors, and semiconductor in terms of energy bands. Okay, but there is no conduction in forbidden band gap. Okay, which is the difference between the conduction and the valence band. So the electrons cannot exist within the forbidden band gap, and that is shown in figure 1.4b. You see either it is in the valence band or in the conduction band. So for 1.4b qualitatively shows that an electron from the valence band gaining enough energy and moving into the conduction band. This process is called generation. Okay, and that's how you generate free charge carriers in a pure semiconductor without introducing any impurity, and then you can have the conduction of current. Okay, so as the temperature increases, more covalent bonds are broken and more free electrons and positive empty states are created. Okay, so you see now what happened in this figure 1.5 is that, okay, once you have a breakage of a bond, an electron becomes free from here. Okay, it goes into the, let's say, conduction band, then it's leaving behind a positive state, hole, let's say. Now what happens is that an adjacent or over here you see the adjacent bonded electron in valence band, it might also get thermally excited with temperature, and what it does is it breaks the bond and it occupies the position of the positive hole. Okay, and this hole has the same charge density as electron, so it looks like that the hole is being transferred. The hole is being transferred in this process. So you see a valence electron that has a certain thermal energy and it's adjacent to an empty state may move into that position as shown in figure 1.5. So the position of the hole is changing, right? It's filling up the hole, and it's like hole is moving, So it makes it appear as if the positive charge is moving through the semiconductor. Now this positively charged particle is whole. That's how we termed it. Now in semiconductors, there are two types of charged particles as opposed to conductors. So one is, so both contribute to the current equally. Now we have both, we have negatively charged free electrons, and then we have the empty states that are left behind. So there we have positively charged holes. Okay, so this is another difference in the conduction of current by semiconductors. It's done by both the holes and the electrons. Okay, but since it is a pure semiconductor, it is, of course, it is electrically it's neutral. So we may note that the charge of a hole has the same magnitude as the charge of electron. Of course, it has to be. The concentration given in a volume per cubic centimeter of electrons and holes are important parameter in the characteristic of a semiconductor material because they directly influence the magnitude of the current. Larger number of, if you have a larger number of, for example, charge carriers in a certain volume, you can have a more conduction or more volume of current flow. Okay, with a lesser resistance, you have more concentration. So, an intrinsic or a pure semiconductor is a single crystal semiconductor material with no other types of atoms within the crystal. So, this conduction that we are talking of is of intrinsic semiconductor or a pure semiconductor material. Now, we have a physical relationship between the concentration of this Ni refers to the concentration of either hole or the electrons in an intrinsic or a pure semiconductor, because in an intrinsic the carrier concentration of the free electrons is the same as that of holes. Okay, so this equation it has some constant. You see this capital B is related to the material. For example, for silicon this is 5.23 into 10 to the power 15. Okay, so it doesn't have a very strong, you can say it's not a very strong function of a temperature, but it's a material dependent constant. Similarly, you have the band gap, which is again related to the material in question. Now, silicon has a different band gap as compared to, for example, gallium arsenide or germanium. Germanium has a lower band gap. So, for example, germanium as a material doesn't require much energy. I mean, a single crystal of germanium might generate more charge carriers in conduction band easily as compared to silicon due to the lower band gap. But then these values, band gap and this band gap is in electron volts. It's energy required for electron to jump from one valence band to conduction band. This is an energy parameter. The other parameter is related to the material, okay, of a semiconductor, whether it's element or it's a compound semiconductor. So B is a coefficient related to the specific semiconductor material, and E.g. is the band gap, electron volt. T is the temperature in kelvins over here. K is the Boltzmann constant, so it's constant. E is the exponential function. Okay, so in intrinsic semiconductor, the densities of electrons and holes are equal since they are thermally generated electrons and holes are the only source of such particles. So we have this notation to, in terms of the material constants, capital B, e.g. the band gap, and then temperature. How much it gives an indication of how much carrier concentration is of holes and electrons in the material, in the single crystal pure intrinsic semiconductor material that can conduct the current in conduction band. So the values of B and G for several semiconductors given in table 1.3 as over here, and you mind that the band gap and the coefficient they're not dependent on temperature. The intrinsic concentration Ni is a parameter that often occurs in the current voltage relationship for semiconductor devices. Now here is an example. It's a simple example. What it says is to calculate the intrinsic carrier concentration for silicon. So you see the material is silicon, you have given the temperature. So in order to calculate the concentration of the electrons and holes, which are of course equal. Now you can just plug in those values for silicon. So T is 300 Kelvin, so you can bring this. So this is T is 300 over here, and you have the Boltzmann constant. Okay, then the band gap is 1.1, as we can see from table 1.3. So this is 1.1 for silicon. B is 5.23, 10 to the power 15. So if you plug those values over here and this equation for silicon and with the temperature and the band gap values of silicon, you get to know that okay. In a per cubic centimeter volume, we have the concentration of charges, free charges, as 1.5 10 to the power 10, and that is primarily due to 300 Kelvin temperature that we have generated free charge carriers, right? Now, the comment is that an intrinsic electron concentration, it might look 1.5 into 10 to the power 10 per cubic centimeter, a large value. However, if you consider the number of atoms, of silicon atoms that are in the, for example, in this structure, the number of silicon atoms, and let's say this is my 1 cubic centimeter. Okay, I'm just saying that this, let's say this is a 1 cubic centimeter volume. The number of atoms are much larger as compared to the number of free charge carriers, you see. So that means the generation of current or conduction of current is not that high in a pure semiconductor material. So it's not a very good conductor. You see, an intrinsic electron concentration at this temperature, the concentration of charge carriers that we have in conduction band due to temperature is 1.5 10 to the power 10, and this may appear to be large, but it is relatively small compared to the concentration of silicon atoms, which is much higher, which is 5 into 10 to the power 22. So this value is much higher than the thermally generated charged particles in the same volume, showing that the conduction of current is small in intrinsic semiconductor materials. So in order to increase the concentration Ni for positively or negatively charged, either they are holes or electrons, how you increase this is, one way is to increase some, is to introduce some impurity. For example, we can bring phosphorus or group 5 elements in this crystal, okay, and we can, you see, each phosphorus atom is going to have 5 valence electrons, and it naturally is going to bring a free electron with it, and that's one of the ways you introduced impurity, and then what you have, you're left with is an extrinsic semiconductor material, which we are going to discuss in next video. We have an extrinsic semiconductor with a larger or improved charge concentration in a given volume as compared to intrinsic semiconductor, and that can generate more current for a given thermal or electrical conditions. Okay.